Hello, everyone. My name is Tomohiko Uyematsu. I am from Tokyo Institute of Technology. Today, I'd like to give you a talk. First, I'd like to show you my slide. My talk is about the data compression principles and applications. First of all, I'd like to introduce my research field. My research field is the information theory. Then, what is the information theory? The information theory is the mathematical study of the quantification, storage, and communication of information. This theory was established by C. Shannon in 1948. Okay, next I'd like to explain a little bit about the overview of information theory. Information theory is divided into two parts, mainly two parts. First part is the source coding, and source coding deals with the limit of data compression. And this part is concerned today's talk. Okay? And another part of the information theory is the channel coding. Channel coding treats the limit of transmission rate for reliable communication through noisy channels. And as I said before, source coding is almost equal to the data compression. And the data compression is divided into two parts. First one is the lossless data compression. Lossless data compression means that we can recover the original data from the compressed data. Hence, this compression is used for the data and program. And in this case, the limit of compression is given by the entropy of the source. Okay? Another compression method is called the lossy data compression. In case of the lossy data compression, we cannot recover the original data perfectly from the compressed data. However, if we cannot distinguish the difference between the original data and the recovered data, then sometimes it's okay. For example, in case of audio or picture or videos. And by using this kind of the differences, we can much more good performance, compression performance than the lossless data compression. And in case of the lossy data compression, the limit of compression is given by the reddish of a function. But today's talk, I only explain the lossless data compression. Okay? The contents of my lecture is as follows. First, I'd like to explain the principles of source coding, which is the mathematical background of the data compression. And second, I'd like to explain the Huffman code, which is the optimal code. And third one is the Lempel-Ziv code, which is the most famous and most popular coding for the techniques for the computers. And lastly, I show you the compression experiments. Okay. Now I'd like to start with the principles of source coding. Okay, first I'd like to start with the information source. And the information sources produce a sequence of symbols, say x1, x2, so forth, with a given probability. Okay, so what is the example of the information source? This is this slide shows some examples. First one is the sequence of numbers that comes out when you roll a dice. Okay, I roll a dice. Okay, I get number 1, and again roll a dice. I get the number 3. And this kind of sequence is example of the information source. Another example is the sequence of heads and tails obtained by flipping a coin. It's almost similar to the dice. Okay. Another one is the stock market index series every minute. Okay. And hourly temperature in Tokyo. These are the example of the information source. Okay. And the information sources are classified as follows. A source may be modeled as a memoryless, finite state, ergodic, stationary, or general in order of increasing generality. Okay? But in this talk, I mainly talk about the memoryless sources. And later, I touch upon the stationary ergodic sources. Okay? So we first start with the memoryless source. For memoryless sources, a sequence of lengths n, say the x1 through xn, okay, has an occurrence probability that the occurrence probability of the length n sequence is given by the product of each symbols. Okay, the occurrence probability of the first symbol x1 and occurrence probability of the second symbol x2 and the occurrence probability of the last symbol An example of this memoryless sources, there's a sequence obtained by rolling a dice. Okay. Next, I'd like to explain the code for information sources. Okay, let alphabet X be a finite set, and alphabet X denote the output or symbol of the source. Okay, and symbol is denoted by the X. Okay, and code is C is a mapping from the alphabet to a sequence of 0 and 1. Okay, and code word for the symbol X is denoted by the C of X. Okay, and from now on, we only consider the non-singular code. Non-singular means that two symbols are different, then corresponding code words are also different. Okay. Here's some example of code. Assume that the alphabet consists of the four letters A, B, C, D, okay, four symbols A, B, C, D. Okay. For the symbol A, in the code C1, A is mapped to the code word 00, okay? And B is mapped to the 01, and symbol C is mapped to 10, and D maps to 11, okay? In this case, the length of the code words are the same, okay? And so the C1 is sometimes called a fixed length code. Okay, here's another example, C2. Then symbol A is mapped to 1, and symbol B is mapped into the 10, and shift to 100, D to 1000. Okay. In this case, the length of the code was differs depending on the symbols. So this kind of code is called variable length code. Okay. And C3 is also an example of the variable length code. Okay. Okay. Next, I'd like to show you the length function of code. A length function denotes a mapping from the alphabet to the natural numbers. And L of x, the L of x, I mean the length function for the symbol x, is given by the bit length of the code word corresponding to x. Okay? Note that the length function depends on the selection of the code. Okay? So if we change the code, the length function will change. Here's an example of the length function. We picked up the code C3 here. In code C3, the symbol A is mapped to 1, and B to 01, C to 000, D to 001. Okay? In this case, the length function goes like this. For symbol A, the length function is 1. For the symbol B, the length function is just 2 bit, so the 2, okay? And so forth. Okay? Next, the performance of criteria of code. And usually, as a performance criterion of code, we use average code length given by this figure, this equation. Okay? Average length is given by the occurrence probability of the symbol x multiplied by the length function for the symbol x and taking a sum of all the symbols. This is the most important measure for the lossless compression. Here's an example of average code length. We also assume that the alphabet consists of the four symbols, A, B, C, D. And all these symbols have the same occurrence probability, 1/4. Okay? And okay, let's pick up the first code, C1 for X. Okay? In this case, this code is a fixed length code, and all code words has length 2. Okay? And in this case, the average code length is given by 2. Okay. Okay. In another example, we pick up this code, C2. Okay. In this case, the length function is given by 1, 2, 2, 3. Okay. Hence, the average code length is calculated by as follows, and also 2 bits. Okay. Here's my example. Here's another example here. An example of average code length for the biased case. The alphabet is the same as before. The occurrence probability of A equal to half, and that of the B equal to 1/4, and the occurrence probability of C and D are 1/8. In this case, okay, we will first pick up the fixed length code. In this case, obviously, the average code length is 2. Okay? But if we pick up this code, okay, the average code length is given 1, 2, 2, 3. And the average code length is given by 1.625, and which is smaller than that obtained by this fixed length code. Okay? So this example shows that the code which minimizes average code length depends on the probability of symbols. So depending on the probability of symbols, we have to design a good code. Okay? That is the important things in the information, in the source coding theory. Okay? Next, I'd like to explain another viewpoint of the source code data compression. Let us consider the encoding of a string over the alphabet sequence, okay, A, B, C, D. For example, this kind of sequence, BA, BC, A, C, C, D, BC, okay. Here's one condition for the encoding. And encode each symbol repeatedly by using one code. Okay? This is a condition. So first we encode the symbol B, and then we encode the symbol A, and after that we encode the symbol B. So we repeatedly by using one code. Okay. Okay, here's one example. If we use a code C2 here and encode the strings AD and BC, okay, strings with length 2, and A is encoded into 0 and D is encoded to 110. So AD is encoded into 0110. Okay. On the other hand, B is encoded to 01 and C is encoded to 10. Hence, BC is encoded into the 0110. So these two sequences of code words are identical and identical. So from the sequence of the code word 0110, we cannot uniquely decode the encoded sequence. Okay? We cannot decode the code words uniquely. And in this case, we need the comma to know the end of the code word. So in order to encode symbols repeatedly by using one code, we need to know delimitations between code words. Okay? So what condition should be imposed on the code word to know the delimitations? Here comes the answer. Okay? So here comes the prefix code. In the prefix code, two symbols are different, say A and B are different. So the code word for CA does not coincide with the prefix of the code word of B. I mean the beginning part of the code word of B. For example, the prefix of the 011 is 0 or 01 or 011. Okay? I will show example. In this example, the code C1 and C3 are prefix code. Okay? For example, in case of the C1, I'm the fixed length code. The symbol, okay, the code word for the symbol A is 00. Okay? But there is no other code word begins with the 00. Okay? So the code C1 are prefix code. And in case of the C3, okay, the code word for symbol A is 1, but other code word does not begin with 1. In a similar manner, code word for 01, other code word never begins with the symbols 01. Okay. However, in case of the C2, A is encoded into a code word 1, but 1 is the beginning part of the code word of B. Hence, C2 is not the prefix code. Okay. In order to represent the prefix code, we introduce a code tree. Okay. First, I'd like to explain a little bit about the name of, about the concept of the graph theory. Okay. Okay. In the graphs, there's a node and edge. Okay. Edges connect two nodes. Okay. And there is a root here. Okay. And the direction of edge goes upwards. Okay. And from each node, at most two outgoing edges from each node. Next, and the node without outgoing edges is called leaf, okay? And the node with outgoing edges is called inner node. Okay? And from the root, this leaf has a level 1 because from root, we follow the one edge and come to this node. And this leaf has a level 2 because in order to reach this node from root, we have to follow the two edges. Okay? So the number of edges from the root to that leaf or node is given by the level of that node. Okay. Okay. Here's a review. There's a special node root. Okay. And there's a node, there's edge, and leaf is a node without outgoing edge. Okay. And there's a level. Okay. And next, I'd like to explain the labels for edge and node. And two outgoing edges have labels 0 and 1. And usually, the left outgoing edge has label 0, and right outgoing edge has the label 1. Okay? And a label for node is obtained by following labels of edges from the root to the node. Okay? So this leaf has a label 1, because from root, we only follow the edge with label 1. Okay? And this leaf has label 0, 1. Okay? And this inner node has a label 0, 0. And similarly, this leaf has a label 0, 0, 0. Oh, sorry, this one should be 0, 0, 0. Okay. And every code can be represented by using this tree. Okay? For example, a tree representing C1 is given like this. And from now, we write down the tree from upside down. Okay. And in case of the tree representing the code C1, four code words is 0, 0, 0, 1, 1, 0, 1, 1. Okay. And all code words correspond to leaves. Okay. And in case of the C3, okay, at that time, code word is 1, 0, 1, 0, 0, 0, 0, 0, 1. Okay. And again, the all code word corresponding to leaves. Okay. But in case of the C2, the code type is 0, 0, 1, 1, 0, 1, 1, 0. Okay. Then code word 0 does not correspond to a leaf, but an inner code. Okay. Since 0 is a prefix of the 0, 1, so 0 is in the inner node. Okay. So from the definition of the prefix code, if two symbols are different, then the C of A does not coincide with the prefix of the other code word C of B. Hence, for prefix code, all code words must be correspond to the leaves. Okay? So if we write down the code tree, we can distinguish this code is prefix or not. Okay. And also the decoding of prefix code can be done in the following way. Okay. Let us consider the decoding of prefix code C3. Okay. The code tree for the C3 is given like this. Okay. And decoding of 0, 1, 0, 0, 0 goes like this. Follow the edges from the root according to 0 and 1. So follow 0 here, and next symbol is 1, so follow 1. So we come to the leaves, and this leaf corresponds to the symbol B. So 0, 1 is decoded to B, and return to the root. Okay, and next symbol is 0, so come to 0. Next symbol is 0, and last symbol is also 0, and we come to the leaf, and this leaf corresponds to the symbol C, so the 0, 0, 0 is decoded into the C, and so forth. Okay, by using the binary tree, we can easily decode the prefix code. Okay, so here comes the important inequality. A length function L of prefix code must satisfy this inequality. Okay. 2 to minus L of x, taking the sum of all symbols, is less than 1. Here comes an example of Kraft inequality. Okay. I picked up the previous code, C3 of x. Okay. The code was goes like this. And its length function is given by 1, 2, 3, 3. And 2 to minus length function of x is given by 1 over 2, 1 over 4, 1 over 8, 1 over 8. And taking the sum of these values, we obtained 1. So this code satisfies the Kraft inequality. Okay. Okay, I'd like to show you the proof of the Kraft inequality. Okay. All code words of prefix code corresponding to the leaves of tree as a definition from the definition of the prefix code. Okay. And assign the weight 2 to minus L of x to each leaf corresponding to the code word. Okay. So in this case, 1 over 8 here and 1 over 4 and half here. Okay. Next, determine the weight of inner node as the sum weight of its children nodes. So this inner node has a weight sum of the 1 over 8 and 1 over 8. So 1 over 4. Okay. In this inner node, the sum of 1 over 4 and 1 over 4. And in this one, the sum of 1 over 2 and 1 over 1. And since the weight of inner node at level L is less than 2 to minus L, because some leaves is not assigned to the code word. Okay. Hence, the weight of root is less than 1. This completes the proof of the Kraft inequality. Okay. And much more interesting thing is that there is a converse of Kraft inequality. That is, if a length function L of x satisfies this inequality, then there exists a prefix code which has a this length function L of x. Okay. So if the length function satisfies this inequality, then there must be a prefix code with this length function. Okay. Okay. The proof of converse is given by an example. Okay. Let us consider the alphabet. It consists of A, B, C, D, and consider a length function. L of A equals 1, and the other lengths for the symbols C, B, C, D are all equal to 3. And in this case, the Kraft inequality is satisfied. Okay. They assign code word in the order of smaller code length. Okay. The smallest code length is 1. Okay. So make a complete binary tree with level 1. Okay. This one. And pick up the one leaf and assign it the code word for A. Okay. And next smallest code length is 3. So extend the nodal leaves which are not assigned. So this node to assigned code word to level 3. Okay. And among them, we pick up to 3 of them and assign the code words for the B, C, and D. And as a result, we obtain the following code. And this is the proof of the converse. Okay, here comes one most important result in the areas of the information theory. This is called the source coding theory. Let P of x be the occurrence probability of x. Then for any prefix code, we must have the average code length is greater than or equal to the entropy of the source, where the entropy H of P is given by the probability of x symbol x log 2 probability of symbol x, taking the sum of all symbols and taking the negative sign. So the average code length has its limit. Okay. And limit is given by the entropy. And conversely, there exists a prefix code satisfying that average code length is less than entropy of source plus 1 bit. This is the source coding theorem. And in fact, we can construct a prefix code which has its length function minus log 2 occurrence probability of the symbol x and taking the ceilings. And ceilings denotes the smallest integer greater than or equal to z. Okay. First, I'd like to show you an example of this theorem. Okay. Again, the alphabet is here. And the occurrence probability for A, B, C, D is given by 1 over 2, 1 over 4, and 1 over 8. In this case, the entropy of the source is given by the 1.75. Okay? And if we pick up the fixed length code C1, then its average code length is 2, and which is greater than or equal to 1.75, which is the entropy of the source. Okay, theorem holds in this code. Okay, and if we pick up the C3, okay, in this case, the code word goes like this, and length function is given like this. And in this case, the average code length can be calculated like this, and we obtain the 1.75, and which is equal to the entropy of the source. As I explained before, entropy is the limit, the smallest value of the average code length. Hence, this code is optimal from the viewpoint of the average code length. Okay, here's another example. The alphabet is the same, and all the probability of symbols are equal. Okay? And in this case, the entropy of the source is given by 2 bits. And if we pick up the fixed length code, then the average code length equal to also 2, and which is equal to the entropy of the source. So this means that the C1, this fixed length code is optimal from the viewpoint of the average code length. Okay. And again, we pick up the C3, the variable length code, as before. And in this case, the average code length equal to 2.25, and which is greater than the entropy of the source, 2. Okay. So as I said before, the optimum code depends on the occurrence probability of the symbols. Okay, now I'd like to show you the proof of theorem 1. Let us consider an inequality. Log 2x is smaller than or equal x minus 1 log 2e, where the equality holds when x equals 1. This inequality it can be proved by using this figure. Okay? This curve shows the log 2 of x, and this line shows the x minus 1 times log 2e. And this line is tangent to log 2x at x equals 1. Okay? And if we need a more rigorous proofs, you can do it by using elementary calculus. Okay? Okay, let us start the HP minus average code length. Okay, from the definition of entropy and from the definition of the average code length, we have the next equation. And if we write down L of x to the log to 2 minus Lx, we can write down the here. Okay? And in the last expression, by using the given equation, inequality here, this log 2 part, okay? And by multiplying px for each terms and taking a sum for the last time, we obtain this equation. And in this equation, since the prefix code satisfies Kraft inequality, so this summation must be less than 1, so 1 minus, which is equal to 0. And this shows the first part of the theorem 1. Okay. Next, I'd like to show you the last part of the theorem 1. For a length function given by this one, okay, occurrence probability of P of x, taking a log and taking a negative sign and taking a series. Okay? And in this length function, 2 to minus L, this length function is is smaller than or equal to 2 to log 2 P of x, and which is equal to the occurrence probability of x. And by taking the sum of it, we obtain that this length function satisfies the Kraft inequality. Okay? Since the length function satisfies Kraft inequality, there exists a prefix code which has the least length function. Okay? And the last part is average code bound on the average code length. Okay. For a code with the less length function has the average code length here, this one. Okay. And the ceiling is can be upper bounded by the minus log p of x plus 1 and multiplying the p of x and taking the sum for the last part, we obtain the this bound. Okay. This completes the proof. And this theorem 1 holds not only for symbol-wise codings, but also the block-wise coding with block length n. I mean, not the symbol by symbol, but the n symbol block by block is also, we can apply the theorem 1. Okay. Here's the block-wise code. A code Cn is a mapping from the sequence of length n to the sequence of 0 and 1. Okay. In this case, the length function, we write down the Ln. Okay. And Pn denotes the probability distribution, not the sequence of length n. Then we must have that average code length is greater than or equal to h of Pn, which is called the nth order entropy. And nth order entropy is given by the last line of this. And conversely, there exists a prefix code, which has a length function, this one, and satisfying, again, the nth order entropy plus 1. This theorem can be proven by replacing the probability to one symbol to the blockwise. Okay. And from this theorem, we can see that there exists a prefix code such that its average length per symbol, this one, satisfies this inequality. And in this case, this value is called entropy per symbol. So the average length per symbol is in between the entropy per symbol and entropy per symbol plus 1 over n. Okay. And especially for memoryless sources, we have that the nth order entropy equals to the n times of its entropy. And in this case, this implies that average code length per symbol can be upper bounded by the entropy plus 1 over n, where n is the length of the block. This means that the average code length per symbol approaches to the entropy of source as the block length tends to infinity. Hence, from the viewpoint of efficiency, the block coding is much more efficient than the symbol-wise encoding. Okay. Okay. Now the fundamental principle of the data compression is over. And I'd like to move on to the practical codes for data compression. First one is the Huffman code. Okay. And what is a Huffman code? A Huffman code is a prefix code, which minimizes the average code length. Okay. And the procedure to construct the Huffman code goes like this, but a little bit complicated. So to make the long story short, I'd like to explain how to construct the Huffman code by using an example. Okay. Here's an example of the construction of Huffman code. Okay. And there are 5 symbols in the alphabet, A, B, C, D, E. Okay. And almost all symbols have the equal probability, but only E has the probability 1 over 3. Okay. Other symbols have probability 1 over 6. Okay. The first procedure is that arrange symbols in decreasing order of probability. So the maximum probability, the symbol with maximum probability is E. Okay, so E is first, and other symbols have the same probability. Hence, in any order, it's okay. So in this case, I use the alphabetic order A, B, C, D. Okay, and select 2 symbols with the smallest probability and replace them with 1 new symbols. Okay, so Among them, we pick up two symbols, two smallest symbols, say C and D, okay? And replace them with one new symbol, say alpha, okay? And use the sum of probabilities of two symbols as a probability of the new symbol. So this alpha has a new probability, 1/3, okay? Then arrange the symbols of the newly obtained alphabet, again in decreasing order of probability. So new alphabet is E, A, B, and newly added symbols, alpha. So we rearrange the order and E alpha A, B, okay? Then repeat the procedures 2 and 3 until there is finally one symbol with probability 1. So among these alphabet, the two smallest probability, symbol A and B have two smallest probabilities. So we merge them together and a new symbol, beta. And this beta has a probability 1/3, okay? And the new alphabet is E, alpha, and beta, okay? And we pick up alpha and beta, and we merge them together and new symbols with probability 2/3, okay? And lastly, is this gamma and E is merged into a new symbol, delta, and with probability 1, okay? And last step is that the code tree can be obtained by creating a tree corresponding to the above procedures, okay, and adding different labels of 0 and 1 to 2 edges, extending from each inner node, okay. We assume that new symbols corresponding to the inner node and put the labels 0 and 1 here, okay. Then, considering this as a binary tree, we can obtain the as code word assignment. For example, symbol E has a code word 1, okay? And symbol A has a code word 0, 1, 0, okay? Symbol B has a code word 0, 1, 1, 0, 1, 1, and so forth. Okay, here's another construction of a Huffman code. In this case, all symbols have equal probabilities. Okay? And taking these two probabilities, merge here, 1/2. And the next smallest two probabilities, one here and here, A and B. So merge here. And merge two nodes here. And put the labels for each node, each edges, and we obtain the following code bus. Okay. This is nothing but the fixed length code. Okay. The next theorem shows the optimality of Huffman codes. Okay. The Huffman code gives the minimum average length among prefix code, and its average code length satisfies the following inequality, where the Pmax denotes the maximum probability for the symbols. Okay. And if the Pmax is greater than half, the average code length is less than entropy plus Pmax. As in other cases, the average code length is less than entropy plus Pmax plus 0.086. Okay. And we can also consider the blockwise Huffman code. Okay. If we construct a blockwise Huffman code for xn, I mean the sequence of length n, we need the m to n symbol probabilities. M denotes the size of x. But this is computationally impossible for large n because it's an exponential order for the length n. Hence, the blockwise Huffman code is not practical at all. And usually, instead of the Huffman code, we use the arithmetic code instead of the Huffman code. But because today the time is limited, so I cannot explain the arithmetic code. I'm sorry. Okay. Next one is the Lempel-Ziv codes. Okay. What are Lempel-Ziv codes? Lempel-Ziv codes are most famous and most popular data compression algorithms And there are so many software implementations from for almost all OS. In case of Unix, famous one is Compress or the gzip. Okay? In case of Mac OS 10, Zip or Compact Pro. Okay? In case of Windows, there is a tool called Zip. Okay? And there are two versions of Lempel-Ziv code. And Lempel-Ziv 77 code, we call it LZ77 in short. Okay? And this code uses already encoded input string as a dictionary. Another one is a Lempel-Ziv 78 code called LZ78 in short. Okay? And this code parse input string by using a tree and use it as a dictionary. And both algorithms look like, but different. Okay? And there are two special features of this Lempel-Ziv code. And both algorithms do not need the probability distribution of source in advance. In case of Huffman code, we need the probability distribution of symbols before we construct the code. Okay? But in case of the Lempel-Ziv code, we do not need to know the probability distribution. These two algorithms only depend on the input sequences. Okay? And both average code lengths per symbol converge to the entropy of the source as the block length tends to infinity. That is the nature. That is from this nature. From this feature, the Lempel-Ziv code are called the universal code. Okay? So if we increasing the length of the input sequences, then the average code length per symbol of the Lempel-Ziv code approaches to its optimum value. That is the entropy of the source. Okay, okay, let us start with the LZ78 code. Okay. And LZ78 code is based on the incremental pattern. And parse and input sequences into substrings, satisfying the following two conditions. Okay, here's the incremental parsing. First condition is that all substrings are different, okay, except last substring. Okay. And condition 2 means that j substrings, Sj, excluding the last symbol, coincides with one of the substrings previously obtained substrings, say S0 through Sj minus 1. Here we assume that the S0 equal to null string. Okay? Here's an example of incremental parsing. For an input strings AB, AB, BA, 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 AA. Okay? And its incremental parsing goes like this. A, B, A, B, B, A, B, A, B, A, A. Okay. This can be in the following matter. First symbol A does not appear as a substring before, so only A. And next symbol B is not appeared in the substring, so B is here. Next symbol A is appeared here, but AB is not appeared, so AB is the next substring. Okay, and next one B is appeared here, but BA is not appeared, so BA is the next substring, and so forth. And in the last part, okay, A is appeared here, AA is appeared here, but this is the last substring, so AA is okay. Okay? That is. And this incremental parsing can be done by using a tree. Okay? And to make the complicated, in order to avoid the complicated things, we only consider that the alphabet considers consists of the A and B. And the encoding rule of symbols is A is encoded to 0 and B is encoded to 1. Okay? And first, as a preliminary part, label the root with number 0. Okay? 0. And 0 corresponds to the null string. Okay? And extended edges corresponding to each symbol, A and B. Okay? And parsing of the first substrings and its encoding like this. The input sequence is A, B, A, B, B, A, B, A, B, A, A, as before. And read symbols in the strings, input strings, and follow the edges corresponding to symbols from the root to a leaf. So read A and follow this edge and come to the leaf. Then A is encoded in the following way. A is null strings followed by A. And null string corresponding to the node with label 0. So 0A. And in this case, only null string is referred. Hence, only A is encoded. So C of A equals 0. Okay. Then we update the tree. Add label 1 to the node corresponding to A. Okay, this one. And extend the edges from each symbols. Okay, for each symbol, A and B. Okay, the next symbol is B, so follow the B, and comes here, leaves, so stop it. Okay, and this means that B is null string followed by B. Okay, and there are two possibilities of the previous substrings, null string or A. So in order to distinguish this difference, we use a 1 bit to represent this 0. So 0, 1 is a code word for it. B is encoded into a code word 1. Okay. Then again, add the label 2 here to the node corresponding to B and extend it edges for each symbol. Okay, A. Okay. The third substring goes like this. A follow here, but this is the inner node. So we need one more symbol, B here, and we come to the leaf. Okay, and this AB is substring A followed by B. Okay, and substring A is numbered as 1. Okay, 1 and B. Okay, and in this case, there's a 3 possibility of the previous substring. So we need 2 bits to represent this number 1. So it's 0, 1, and B is encoded into the 1. 0, 1, 1 is a code. Okay. And the fourth substring is almost the same. B comes to here and A comes here. Okay. So substring B followed by A. Then B has the label 2. Okay, here 2. And there are 1, 2, 3, 4 possible substrings. So we need 2 bits to represent this 2. Okay, so the 1, 0. And A is encoded into the code word 0. And so forth. Okay. Here's the LZA78 encoding of the input sequence. Okay, as I explained, A is encoded into 0, B is encoded into 0, 1, AB to 0, 1, 1, BA to 1, 0, 0. And this is the sequence of it. Okay, this is the encoding. Then how about decoding? Okay. Decoding of LZ78 code goes like this. Code word length for the J substring of S of J is fixed because this is the index part, log2j taking the ceiling, plus last symbol, log2 size of the x taking the ceiling. And we can find the delimitation of the code words corresponding to all substrings in advance. Okay. And for example, the sequence of code words here, we can delimitate the code word in the as follows, okay, by using this equation. Okay. And as before, the last 1 bit denotes the last symbol. Okay, and the rest of this symbols shows the index of the substring. Okay. Okay, so the first code word is 0, and in this case, this is corresponding to the symbol A. And substring null followed by the A, and first substring is recovered as a A. Okay. In the second code word, 0, 1. Then 1 corresponding to the B, symbol B. And 0 denotes the null substrings. So null substring followed by B. And the second substring is B. Okay. The third code word is 011, and 1 corresponding to B, and 01 denotes the index for the substring S1, which is corresponding to A. So A followed by B is the third substring. And fourth code word is 100. Okay, 0 denotes the last symbol is A, and 10 denotes the substring S2, which is equal to here, B. So B followed by A is the fourth substring, and so forth. And we can recover the original sequence. The next theorem shows the average length of LZ78 code. Okay? For any stationary ergodic source, which is a generalization of the memoryless source. Okay, Pn, the average code length per letter is upper bounded by the nth order entropy divided by n plus this term, where C1 is some constant. Okay? And comparison with the theorem 2 goes like this. In case of theorem, there exists a code satisfying this inequality. But in case of the LG78 code, this part is different. Okay? In case of theorem, this upper bound is tight compared with the LG78 code. I mean that 1 over n is smaller than this pair. However, in both cases, as n tends to infinity, this term vanishes, and both code approaches to the optimum value. And another comment is that what are stationary ergodic sources? And in case of stationary ergodic sources, satisfy the following two properties. First one is the stationarity. This means that the occurrence probability of any substring, for example, the AB or that, does not depend on its position. Okay? Next one is the ergodicity. The relative frequency of a string in the sequence converges to its occurrence probability as the length of sequence tends to infinity. So, by observing the long sequence, we can estimate the original occurrence probability of the source in case of the ergodic sources. And the stationary ergodic sources satisfy these two conditions. Okay? And one typical example of the stationary ergodic source is a memoryless source. Okay? But the stationary ergodic source is much more general. Okay. Next, I'd like to explain the LZ77 code. Okay. The LZ77 coding goes like this. Here's the already encoded subsequence. And this yellow box shows the sliding dictionary. Okay. And this part is the subsequences to be encoded. Okay. The encoding of the substrings goes like this. We find the longest match in the dictionary from this first part. Unencoded part. Okay, so BAB is appeared here, but BABA not appeared in the dictionary. So BAB the longest match. And next we pick up the unmatched symbol, next one symbol, A. Okay, and encoding a substrings, this BABA, into a triple. Okay, and first number 1 denotes the match position in the dictionary. So BAB start from the 1, position 1 in the dictionary. And next 3 means the match length. So match length is 3, BAB. Okay? And last symbol is the unmatched symbol. Okay? And encoding of the next substrings. First, slide the dictionary to include the encoded substrings. So we shift the dictionary 4 symbols. Okay? So 4 symbols come going out from the sliding dictionary and enters another new 4 symbols. Okay? And subsequence to be encoded is here. Okay? Next, by using this dictionary, we encode the next substrings. Okay, A is here, but the A is not appeared. Okay? So find the longest match is A, and unmatched symbol is A. Okay? And AA is encoded to a triple 1 match position in the dictionary here. Okay, and match length is 1, and unmatched symbol is A. Okay, and again by sliding the window, and the next symbol is C, but C is not appeared in the dictionary. Okay, so the encoder substring C into a triple, say, first one is at arbitrary position in the dictionary. Okay, anything from 0 to 5, anything is okay. And match length is 0. Okay, unmatched symbol is C. Then, what shall we do if there's no sequences in the sliding window, sliding dictionary? So this happens when we encode the first substance. Okay, no encoded substance here. In that case, put an arbitrary sequence as an initial dictionary. Okay? And this sequence is shared with the decoder. So if we share these sequences between the encoder and decoder, then the encoding process can be done from the first substance. Okay? Next, how to decode the substring. And decoder substring BABA from a triple, it goes like this. Okay? But first, one denotes a match position in the dictionary. So match position here. And match length is 3. So taking the 3 BAB string, length 3 strings BAB here. And copy this substring and append the last symbol A. Okay? So from the 1, 3A, we can recover the original sequences, as long as the sliding dictionary are identical. Okay? And representation of code word is obtained in this following way. In this case, we assume that the dictionary length is 6, okay? And the maximum match length equal to 6. But usually the dictionary length is from 2 to 10 to 2 to 14. Okay? And maximum match length is as many as 256 or so. And each symbol can be represented with 2 bits. And usually, in usual cases, 8 bits. And a triple 1, 3A can be, in order to represent the 6 values, we need the 3 bits. And again, in order to show you the 6 values, we need the 3 bits here. And A is encoded in 2 bit and 4. Okay. So 1 is encoded into 3 bit, and 3 is represented by the 3 bit, and last A is encoded to 0, 0. Hence, the sequence of code word is written like this. Okay? And we see that each code word has the same length. This is a special feature of the LZ77 code. Okay. The next theorem shows the average length of the LZ77 code. Okay. For any stationary ergodic sources, PM, the average code length per symbol is less than or greater than the nth order entropy divided by the length of sequence plus distance. Again, compared with the theorem 3, the LZ77 is almost comparable to that of the LD78 code. Okay. Lastly, I'd like to briefly show you the compression experiments. In this section, I'd like to show you the performance evaluation of following code: Huffman code, LZ78 code, and LZ77 code. Okay. As for the benchmark data, we use the Calgary corpus. You can obtain it through this URL. And this benchmark data consists of the 9 different types of text and 5 different types of data. Okay. As for text, the description of the text like this. Okay. Normal English, both fiction and non-fiction, is represented by 2 books, book 1 and book, and 2 papers. Okay. And more unusual types of English writing found in the bibliography, I mean the references, and BIP, and a batch of unedited news articles, and 3 computer programs represented artificial languages. Program for C, program of Lisp, and program for Python. Not Python, but Pascal, in this case. Okay. And the last text symbol is the transcription of the terminal session. Okay. And as for the data, and 2 files of executable code, object 1, object 2, and some geophysical data, geo, and the bitmap black and white pictures, PIC. Okay. Among them, the file geo seismic data is difficult to compress because it contains wide range of data values, where the file peak is highly compressible because of white space, I mean the all zero. The performance of comparison is measured by using a compression ratio. Compression ratio is defined by the ratio of the length of compressed sequence divided by the length of original sequence. Note that the smaller compression ratio, the better the compression performance. Okay, the smaller the better. Okay, and here's the compression parameters for LG77 and LG78. And here's the example of the compression ratio. Okay, Huffman, blue bar is a Huffman code. Green bar is the LG77, and orange bar shows the LG78. As I explained before, the compression ratio is getting better if they have the smaller values. Okay? So from these figures, we can see that the all compared with the Huffman and LG77 and LG78, among them the LG77 or the LG78 is better than the Huffman code. Okay? In a similar manner, program and data also similar. But one example that in case of the only picture, the Huffman code is better than the LG77. Okay. Next figure shows the relation between memory size and compression ratio for the book one. Okay. For the LG77 and LG78, by increasing the memory size, the compression ratio decreases. That is, the performance, compression performance getting better by increasing the memory size. Okay. And in this example, that the LG78 is much better compression ratio than that of the LG77. Okay, last figure shows a comparison of encoding and decoding time for book one. Okay, blue bar shows the encoding time, and green bar shows the decoding time. So, in case of the Huffman code and LG78 code, these two algorithms, encoding time and decoding time, are comparable. But in case of the LG77 code, encoding time is much more greater than that of the decoding time. Okay. So if we use the LG77 code, it is hard to encoding time. So we use only decodings. Okay. That's the conclusion. And this lecture explains the data compression, which includes the forensics, the principle of source coding, mathematical background. And second, the Huffman code, which minimizes the average code length. And third one is the Lempel-Ziv code. And the fourth one is the compression experiments. Okay. Okay, that's all my lectures. Thank you very much for your listening. If you have any questions, please give me the chat or the Q&A. Okay. Is there any question? There's one question. Okay, I'll read down this. Thank you very much. In the future, do you think AI helps to improve compression? That is an important question. And from my viewpoint, if we can know the, if we can know the statistical property of the source, its performance is limited by the entropy. However, for example, if we only one data, long data is given, then we cannot know statistical property of that data. And so in such a cases, AI may helps to improve the performance, but I'm not sure. Okay, now I'd like to finish my talk. Thank you very much for attending this lecture. Thank you very much.